Okay, so welcome everyone to HAO colloquium. Today's speaker is Fazul Laskar, and he's currently a research scientist too at the Laboratory for Atmospheric and Space Physics at CU Boulder. And he did his PhD in space physics at the Physical Research Laboratory in Ahmedabad, India in 2014. And then he went to Germany, where he worked at the Institute of Atmospheric Physics for 4 years as a research scientist, mainly investigating middle atmosphere dynamics. And since March 2019, he's been working at LASP, mostly for the NASA Gold mission. And his research interest is mainly the atmosphere, ionosphere, thermospheric variability due to forcing from above and below, with an emphasis on space weather studies using whole atmosphere data assimilation. So Fazul, please go ahead. And he will present today on thermosphere investigations using temperature measurements from the Gold mission.
Yeah, thank you, Nick, for the introduction, and thank you, Donglin, for inviting me. Can you hear me very well? I hope so. Yeah. Yeah. So yeah. So in addition to myself working on this, there are a lot of other people, wonderful people contributed. Richard Estes, PI, Gold Mission is here. Thanks for coming. And Michael, thanks for joining. And Nick, also here. And Ben, thanks. And Donglin, online here. Thanks, all of you, and many other our team members. So today I'm going to talk about thermospheric investigations using temperature measurement. So mostly nowadays I work on the data assimilation, but today's presentation, I promise 80 to 90% will be only data, not much assimilation or simulations. So I believe most of you know the Gold mission. It is in a geostationary satellite, SES-14, and this is the Gold instrument or the payload. And this is kind of a cartoon showing what kind of observations, the disk observation we see is like. This is mostly daytime, and as you are going in time, we are covering daytime plus nighttime. So the plan of this talk is initially give some introduction on the Gold mission, and then what are the temperatures like here, mostly dealing with T-disk that we call, and how we derive them, and then use this, how do we use this temperature to retrieve the neutral density. And for this, I will show two different case demonstration. One is like a SpaceX storm, I recall that happened during February 2022. And then we do a similar kind of analysis for the famous Cannon storm, that is the biggest storm of this decade or cycle, solar cycle. And then again, I will use this temperature from Gold to find out what is the most solar or most German solar UV proxy. So it's very important for UV, is very important for ionosphere and thermosphere. So I will use the T-disk to find out which one is the best, to use for thermosphere ionospheric studies. And then I conclude and summarize. So again, Gold is in the SES-14, which is in a geostationary, so it's at the same place all the time over the equator at 47.5, which is the mouth of the Amazon River. And it is the instrument-wise, it is the two identical but independent imaging spectrograph. We call them channel A and channel B. And they cover roughly around 132 to 162. So these numbers varies depending on when we change the gym or rotate the gym. And gym means like rating Yao maneuver or something, I forgot. Yeah.
Got it.
And so measurements that we get are mostly two different kind of modes. One is daytime mode and one is nighttime mode. And from the daytime mode, we get the full disk, because in the daytime we have much bigger signals. So we can cover the whole disk within 30 minutes. Oh, sorry, within 15 minutes, 15 plus 15, yeah, 30 minutes. So, and from the daytime images, we can derive T disk, that is the temperature of the middle thermosphere. And then one of the parameters that we know, we have been using it for several decades, the O by N2. And this T disk is derived from the nitrogen LBH emissions. And O by N2 is from both 1356 and nitrogen. And in addition to that, there are other nighttime observations that I'm not going to talk about here, but these are just listed here. And so I think this is one of the famous cartoon Stan Solomon, former colleague of you here, he made. And this is like showing how the slit, when the slit moves, how we get the spectra. So in the night side, we only have one emission. But once we enter the night side, sorry, day side, we get all the nitrogen band and this 1356 line. So these are we can get with only one channel. So daytime we only use channel A, and nighttime we use both the channels. So this is showing just a cartoon of how we get how we scan the whole disk of the Earth. And this is an actual image or actual irradiance of 1356. And you can see on the left is the day side where we get a lot of all the thermospheric information. And on the right side is the night side. And so this is from the day scan. So that's why night signals are not so strong. But for night side, we do have a dedicated high resolution scanning or high cadence scanning that gives us much better night side signals. So, but for this particular study, since I'm concentrating on T disk, which is obtained only from the day side. So it is a thermospheric observation. And so T disk, how do we get it? So this is a complete spectra of the gold that gold obtains. So this shows like all the spectral lines, the famous one, 1356 from atomic oxygen, and all the LBH bands. So here, this is one that we don't use some nitrogen lines. And so these molecular bands, these are the ones, what they do, how they behave. Like these molecular bands, for example, in this case, one, I think from here, one of these. And so 146, and this is the one. So this one, you can see, as we change the ambient temperature of the atmosphere, the width of the spectral line, width of the band changes, or overall shape changes. So this is an indicator of the ambient temperature. So we can use some forward modeling to derive the temperature. And that's what is explained in these two papers, how we get the T disk from disk images of the daytime. And this is an example of temperature. This is for a date and 30-minute scan. So you can see this is the temperatures over the disk. And there was a minor storm on that particular day. So we see enhancement in higher latitude in response to the energy deposition from the storm. And what are the kind of uncertainties or the random uncertainties that is propagated from the original count rates are shown here. So these uncertainties can be as good as 20 and as bad as 92, or even like close to 100, but I'll show a better picture of the uncertainties. So, and then comes over the disk, the solar zenith angle changes a lot. And there are a lot of implications of solar zenith angle because when we want to interpret the temperature, we have to keep in mind how the SNR changes or the uncertainties changes and how the solar zenith angle changes. So that's what I was telling, like how with the change in solar zenith angle or the local time, the random uncertainties are different. For example, here, 12 local time, around the noon, we have the lowest random uncertainty. And again, these are per pixel uncertainty, so we can combine some more pixels to make them even lower, like close to even single digit. So this is for like about 6 years of data shown here, and with as the solar irradiance or the solar activity is increasing, the SNR gets even better, or the uncertainties are getting better. So as I was telling, like feel free to question. Dong, you have raised your hand.
Yeah, maybe I missed that. So what actually caused those uncertainties? Is that due to the instrument or the model to derive the temperature?
These are propagated directly from the original count rates, the detection rates. So propagated through the retrieval process.
So that's related to the instrument itself, or how
That's
it was
right.
measured.
Yeah,
It's
that's
it's the counting statistics
yeah,
is the limit.
Oh, okay.
yeah. Counting statistics is the limit. Yeah. Yeah, thanks, Dong. And anyone, please stop me. I'm not a very good speaker. I miss very lot of things. So please stop me anywhere. I really appreciate. Yeah, so this is some of these are published here in this AMT paper. So as the solar zenith angle changes, the height of the effective height of the temperature changes. So we cannot like simply say this temperature is coming from a 150 kilometer or 160. So this changes a lot with the solar zenith angle. But in most of the time, like for solar zenith angle less than 50 degrees, we can say this is coming, most of the contribution is coming from 160 kilometer. Again, this is only for low solar activity. And there are other changes with the solar activity, like we usually use one for medium and one for high solar activity and interpolate them in between. So yeah, this is very important for the interpretation or comparison with the model to remember this kind of changes in the altitude with respect to solar zenith angle. And then this is an example of how the temperature changes with respect to local time and with the different time of the year and with the different solar, for example, F10.7, the purple one, the black one is the AP indices. These are the black spikes there are some minor storms. And the color bar again is the temperature. So you can see every time the AP has a peak, the temperature increases, and it increases over all the local times, for example. And there are local time differences that is explained here in this paper. So we can see clearly from here, it responds to both geomagnetic activity and also to the solar forcing here. For example, F10 increased to about 115, and there is a stronger peak in the temperature. So what we do, can we use this kind of temperatures to estimate the neutral density at higher altitudes like 400, 500 kilometers? And that's the exercise that we did using during one of the storm that was a very minor storm, but it was reported that during that storm, SpaceX lost about 40 satellites that was launched on that day. It was 3rd of February 2022, and they lost them during 3rd and 4th of February. So during this event, the satellites or the SpaceX Starlink satellites, they were going through about this kind of orbit. You can see as close to the equator, they were really close to 200 kilometers. And so this is kind of like a very low kind of low Earth orbit, and any change in the drag can significantly impact the satellite altitude and deorbiting kind of stuff. And so we tried this exercise to derive the neutral density during the storm. And some of these indices that we commonly use are shown here. There's IMFBZ, for example, this one, and then solar wind parameters, TST, and AP indices during this time period. So these are the 2 days where the SpaceX launch or deorbiting happened. And so we can see during this time, it was coincident, there was BZ was southward, and then solar wind was not very strong, but still there was some increase. And DST was also going up to about minus 60, and AP indices were about 60. And if you use the NOAA classification, it was only a G1 class event with a max KP of 5+. So it is a minor event, but that caused kind of 38 satellites to be lost during that time. And we tried our gold temperature measurements during that time to derive the neutral density. So these are the about January and mid of the February time. Daytime average neutral density for a given longitude with latitude are shown. And so there is the famously used the F10.7 is also shown here as a black line, and the AP indices are the purple ones, and the gold QB, that is the parameter that we measure with the gold. I'll explain more in the later section. So gold QB is also shown, and we can see there is like considerable difference between the QB and the F10.7 in many places. And I'll explain why there are differences in the last topic of this talk. So overall, we see that whenever there is an increase in the AP index, the temperature is increased, particularly during the storm, SpaceX storm, which occurred here. And so this increased the temperature a lot, particularly in high latitude. And you can see the EUB or the F10 was increased, but it is not, temperature is not responding too much to the EUB or the F10. So it is more sensitive to AP indices in this case, or the geomagnetic storm. And so for this particular, on February 3rd, these are some of the half-hourly scan temperatures, or T-disk is shown. And overall, we can see that the increase in temperatures at high latitude. And if you take a difference with respect to February 1, which is we considered quiet in this case, you can see over the whole disk, it's an increased temperature. So it's globally temperature increased during this time, but more increases towards the high latitude, and that's a pretty good indicator that it's induced by a geomagnetic storm. And if you do like, if it increases over the all latitude simultaneously, that caused by often by solar flux. So in this case, we can see is the geomagnetic condition is the prime driver of the increased temperature. And if we take a difference with respect to quiet day over the whole disk, we see about 61 Kelvin increase in temperature. And we can use this information and convert it to density change using some of the forcing estimation approach. So for example, in this case, we used, as I said, AP is very sensitive. So we varied the AP index in MCs. And this is shown the difference of the temperature from AP equals 8 to AP equals different values. Like, for example, in this case, as we increase the AP, the temperature increases. So with altitude, and then also the density also increases. This is showing the percentage change in density at different altitude. And since we do have a like contribution function, the representative altitude from the gold, so we can use that contribution function and derive the effective temperature from this different kind of runs and find out what corresponds to this 61 Kelvin change that we have seen from the gold. And in this case, we see that the MCS run that is correspond to 160 nanotesla is the one that matches with the gold change in temperature. And that's the run we use. We say MCS gold as this is the run that corresponds to 160 nanotesla somewhere here. And in density wise also it's somewhere in this place. So we use this, and this is the change in density profile shown with respect to altitude. And we are saying this as the MCS gold temperature change in density profile. And in this case, you can see for 200 kilometer, it is about 25% increase in density happened during the storm. This is not much, but for a 200 kilometer, it's probably a big increase like. And if we simply use the native MCS model with all the indices, it shows about like 10%. So it is underestimating the density increase. But with if we use the gold observation and tune the MCS, we get a better answer here. And so let's see how this estimates compares with other things. So in this particular case, I'm comparing with the MAGE model. So MAGE is the geospace model that captures all the geomagnetic solar wind effects more accurately compared to native runs or the free runs. So in this case, we can see that the MAGE change in density profiles matches pretty well with the one that we estimate from the gold. And so, and this bar is showing the range of values possible depending on what reference day you choose. So this is the February 26th. That is like almost 1 week away from the what is on the storm day. And this is February 31. There was some increase in temperature due to some background changes. So we can see all the ranges are possible, but it looks like we can quantify how much is due to solar flux or how much is due to geomagnetic activity. And in this case, we found like due to solar flux, it is about 5%. Most of the increase is due to geomagnetic forcing. And then we also use some validation techniques other than gold. So this is someone else's work. So they showed that the density increase happened is about 50 to 80% in 460 to 500 kilometer, these two altitudes. So these are change in density from swarm data and grace follow-on data. And those numbers, they are pretty close to each other. So, so to summarize, we have seen that we can use the gold temperatures and derive the neutral densities, and which can provide a potential operational real-time satellite drag estimation when we have a real-time gold data. And then this is another case. We are saying the famous Cannon storm or the Mother's Day storm. In this case, we have seen this, the O/N2 was like pretty much very, very kind of never been seen shapes. And that has never been observed before, but like because the gold can see the whole disk together, we saw it for over the whole day of the observation. And so this is O/N2, and let's see, this is the temperature. So this temperature is a bit smoothed here because a bit noisy temperature is. So, and I inverted the color scale here so that you can check the red with red. And so you can see many places where most of the major features match between the O/N2 and T-disk, and that happens during bigger storms. But there are differences, and differences are much bigger during like minor storms. So, and then this is again the grace follow-on neutral density during this storm. So these are the dates of the May 2024. And this is the pre-storm time, and during storm time, we see the temperature increased and also the neutral density increase. You can see here from grace fall on. And if you compare this portion where most of the observations are done, with this portion, we can see about 200% increase in neutral density. And what do we get at 480 kilometer from this? Our estimate is about 180% increase. So this is like we estimated using MC's gold, and here at 480, this is our estimate, and this is the observed one from the grace fall on. So they are pretty close. So they agree very well, our estimates. And so this one was like all our orbit averaged on. So how about along the orbit, how it compares? So we didn't have much coincidence, but this is only coincident with the swarm. So swarm was passing through this location after about 10 minutes, I think, 10 minutes of observation. And this is the nearest coincidence we got. And if you compare like neutral density at 480 kilometer from our method, MC's gold, this is the one we get at 160 kilometers, but we can also get a higher altitude. But in this one, you can see the variation with respect to latitude, like the shapes looks similar in both of them. So can we use like 160 kilometer altitude approximation and say that we can derive the 480 kilometer? And in most of the cases, as we have shown in the previous slides, these are good approximation and they agree very well in the orbit average, but they're also good for like location-wise or latitude-wise. And since this kind of methods can be extended in altitude, this is one example showing how different altitude, latitude, longitude we can get neutral density estimates or change in neutral density. So one caveat still here is like we see big perturbation in the higher altitude, but these are not actually real. And we have to still work on making this, damping this perturbation in the high altitudes. So this method still needs some improvement for use in every location and altitude. So this improvement is still pending. So, but we overall see in orbit average, it works very well. And so this is summary of this Cannon storm that we are seeing. We have seen good agreement between grace fall on and swarm, and also we have seen along the orbit resemblance between them. So again, I'm saying like the same statement I was saying, like if we have an operational real-time gold data, you can provide a operational neutral density estimate or change in neutral density. So yeah, but all this said, the best neutral density estimate could come from the data assimilation. That's the work we have been doing as part of the SWORD Center of Excellence. And this is one example showing like some OC experiments using WACOMX dart. And what is shown here is these are just a pressure level from the top. So 0 means like 500 kilometer and 50 means about 100 kilometer. So the thermospheric temperature you can see here. And this is the true state temperature that we used in the OC. And when we use only the O by N2, we see the highest error. But when we use temperature, the error gets even smaller. But when we use both of them, like combine the blue one, it gets much closer to the true. So this demonstrates that if we use both the temperature and the O by N2, we can get even better estimate of temperature, and which is related to neutral density. And so we can have better neutral density in this case. So yeah, I promise this is the only model results I'm showing here. And now I go to different topic, but related to the temperature, because gold temperature made it possible to estimate or demonstrate that what is the most common UV proxy that we can use for space weather application. And UV proxies, we are pretty familiar. Some of them are pretty widely used in the community and also in the GCM is F10.7, we know it. But we have come across several shortcomings of this, like it is not very good at lower solar condition or higher solar activity condition. So people have tried other proxies like F30, which is a bit better than the F10.7, depending on what you want to use it for. And then also another one is magnesium doublet. We derived another one using the core-to-wing ratio that is also been used in the space weather communities. And there is the other one, why we need them, why you need another one. This has also been used, but not very widely. And in this particular presentation, I'll show, compare them with all these different kind of proxies and show which one is the best. By the way, this QUV, which is integral of 1 to 45 nanometer UV radiance, and that can be derived from the UV or FUV measurements from gold and GUBI. And also you can integrate directly the 1 to 45 nanometer spectra of the solar spectrum, but not all the wavelengths are available at a given time from the solar spectra. So what we do is instead we use empirical model to get all these complete spectra. In this case, the FISM2, which is an empirical flare irradiance spectrum model. So, and in this case, we are also, this QB data from gold are also available in a daily resolution in the gold website. So this is, let's see how it behaves or compares with different other solar proxies. And I'm sorry, this slide is too busy, too many plots. Let me explain what are these. So in this one, showing different QV on the left and F10 and F30 on the right. So these are three different indices shown here. So the FISM2 QV, which is 1 to 45 nanometer integration, is in the blue here, and purple one is our favorite F10.7 index, and black or grayish one is the F30. So we can see already like a lot of differences between them. Like F10 is too spiky, it saturates during low solar condition, and there are other differences like absolute differences also. And this is again the same FISM2 QUB, but in this case, it is compared with the GUBI QUB. GUBI was there for about 7 years in this time frame. And the gold started observation from 2019 till date. So gold observations are in the red here, gold QUB. And MG2 is also shown here in this case. You can see the grayish lines. So overall, they looks pretty similar, MG2 and the other two proxies like GUBI and the gold and FISM. So this is a zoom up of just 90 days or 3 months of data during 2023 in this scenario somewhere here. And you can clearly see like gold QB and FISM QB, the blue and the red, they are going very well with each other. But the other ones, at times you can see big jumps like this one here, this one F10.7. So in shorter times, they have a lot of big deviations compared to these two proxies. These two, FISM2 and the gold QB, they are going very well with each other. So this already shows that like these two are matching, and there are also good resemblance between the F30 and MG2. This F30 is a green one, MG2 is again the grayish one here. But there are at times bigger differences. So this is a qualitative comparison. Let's see how they compare quantitatively. In this case, I'm showing a scatter and correlations for gold versus gold T-disk versus QB. As I was telling, like gold T-disk made it possible to compare these two and see which one is better. And so in this case, we get a very good correlation between them. And note in this case, we excluded all the geomagnetically active times where AP index was greater than 12. So otherwise it gets more scattered, like mostly in the lower part. So in this scenario, we have a very good linear relations between the temperature and the QUB. And again, these are very completely independent measurements, though they are derived from the same daytime scans, but they are independent because one, the T-disk depends on the shape of the spectrum, and QB depends on the intensity of the spectrum. So they are very independent. And then again, if you see the how T-disk compares with the fission to empirical QB, and in this case also we can see a very good correlation between the fission and the temperatures. So there are some like biases, as I was telling in the previous slide. There is this, because of this bias, you can see their inclination is a bit different, and the range is also a bit different. So this bias thing are still under work, and we are resolving, and it's getting better with time. Over the last 2 years, it improved much better. Particularly FISM 2 improved a lot because of this kind of work comparison. And now this is again another busy slide showing all these two plots that I already explained. And in addition to this here, I included F10.7, MG2, F30. So you can see this correlation get worse, or if we go to the, our scatter also get worse. If we go to the F10, and it's a bit better for MG2 and F30, but the best one is this one. Worst one you can see here. And these are some other correlations showing like how F10 compares with all these and all these QB indices like GUBI QB, Gold QB, and FISM QB. And you can see since FISM QB is available for a long time, there are a lot of data points here. And clearly one can see there is an inflection, like once you go beyond 200 solar flux, this linear relationship gets violated. And so same happens here also with gold QB. You can see F10 got, F10 increases too much compared to the other proxies. So it doesn't, it is not anymore linear after 200 solar flux unit. So again, this is based on this analysis, we are saying like QB that we get from gold, and which we also can get from the FISM 2 by integrating the spectrum. We are saying that the QB is the best solar UV proxy compared to any other existing ones. So yeah, this I summarize my talk. We have seen that we can use the gold T-disk to derive the neutral density through forcing estimation technique. And we have seen that the QB is the most germane or pertinent to total UV proxy for space weather applications. And if in some future efforts, we would like to derive the neutral density in 4 dimensions using the combined assimilation of gold and OBN2 and lower atmospheric temperatures from SEBR, MLS, and everything. So with this, I thank you all for your attention, and I'm taking questions.
Question?
I have a question on the proxies there at the end. Do you think that the comparison of these proxies is telling you necessarily that the ones you think are best proxies for solar activity or solar total EUV irradiance, or is it that the T-disk that you measure is better represented by certain proxies? It's not necessarily the same thing to me. Is it really the EUV irradiance, if you had that perfectly, would that be a 1-to-1 correlation with T-disk?
Yeah, so like unfortunately we don't have all these observations, but with the best we have, we are seeing like we can see that the best correlation happens with T-disk. So it is giving us QV is actually is derived the way like it is a representative of 1 to 45 nanometer EUV. And so it is this comparison actually showing us that it is the best proxy. But if we say that can we use the T-disk itself as a proxy, I would say no.
Well, I guess that's not really. My question is, you found the best proxy for calculating your T-disk, but is that the same for correlating with your T-disk? But is that the same as being a best proxy for solar activity?
Yeah, that's what we are saying. It's the best proxy for solar activity. Yes.
I think it just partly depends on what wavelengths you're looking at.
That's right.
So, that wavelength range that it's measuring is giving you a pretty good indication of what at least the integrated is. It doesn't break out the different wavelengths, which
That's right.
PISM does or tries to. Right. But if you get outside that wavelength range, it doesn't tell you anything. Okay.
So what we are saying here is like it's much better compared to f10.7, and it's also in the same daily resolution and like f10.7, and it's also better than the other proxies that we use.
And now we're on this page. So if you correlate with the QUV from PISM, you also see a pretty good slope, right? It may be a shift. or
That's
something,
right.
but-
Yeah, that's coming from this bias here. You see, there is a bias between these two.
Right.
So the gold is the lower one and PISM is the upper one. There is a 20% bias about between them, but it used to be even bigger, but it improved.
Hmm.
So this is getting better with like because of this analysis that we are doing.
It improved because when Philip did this, they went back and looked and realized one of the measurements they were using in their model was basically the data dropped out on them and it wasn't coming in.
For PISM too?
For PISM 2, yeah. So they had to revise the numbers they had out there.
So now they don't have that bias anymore, the shift?
Well, the shift, yes, but if you go back to other plot Fuzzwell, I guess if you look at the scatter, it was jumping up at the higher, some of the higher values of temperature in QEUV, PISM QEUV. So what was happening? So they basically had their model wasn't getting some of the information it needed, and they didn't realize until we saw that we looked at this. Our Oswald looked at this and realized, hey, this isn't matching up. I think the CPI guys were looking at it too and realized we aren't doing very well here. Why not? And they started looking at it. Okay, why not? Was because it wasn't our problem. It was that PISM had some of the data that they were using wasn't a problem with it.
And it seems that we're also using PISM 2. I think both TIHCM and WACOM were getting warmer results than before, warmer temperatures. So maybe there's still I don't know what's the
It could be sound like there's a little bit of a high bias in there for whatever reason.
right.
Yeah.
Well, actually, I have a really like a question on the double vortex on the O2 and 2. I just noticed that the index is like perturbation. Is that a perturbation around the global mean, or is that a perturbation around the mean at each grid point?
It's a great point.
Each grid point.
Yeah.
I see. So if you just look at the original observed O2 and 2, what do you see? I mean,
It's pretty same. It's like
It's the same.
this is still like because the quiet days like O/N2 is pretty much higher here. And so it's even with the absolute O/N2, you pretty much see the same shape.
Usually it doesn't stand out like that.
Oh, okay.
But on this day, you could just look at the raw data and see the structure.
Yeah.
Okay.
We need to keep in mind that what gold is measuring are the effects of the solar radiation, not the solar radiation itself.
In the proxy, yeah.
Yeah, it's a
yeah,
proxy. But,
yeah, it's a proxy. That's why we call it.
Thanks, Michael.
Don.
Sure. Yeah. So earlier about the disk temperature, you mentioned a contribution function or some equivalent attitude, right? Especially, I think there's one slide about the dependence on solar zenith angle.
Yeah.
Yeah.
I'm just
Contribution
curious.
function.
Right.
This
Yeah,
is the
that
one.
part. Yeah. I'm curious if this has to do, I mean, any dependence on like the background density or other conditions. So I suppose it's like some typical conditions. For example, during strong storms like the May storm 2024, would this equivalent attitude still be the same?
Oh, yeah, this is very dependent on the ambient neutral density. It's right. So it will change in response to some of these. Like if the atmosphere get warmer, this will change. That's what happens. Like that's what I was telling. It changes with the solar activity. Same can also happen with the geomagnetic.
Yeah. So basically, we're measuring at a pressure surface.
That's right.
Is the way to think of it. So it's always the same pressure surface, pretty much,
That's right.
regardless.
So yeah, if you go to the pressure surface, it's like it's pretty much same.
Yeah.
It is same.
So sounds like very suitable for TIGCM.
Yes, exactly. It's physically that's what's happening where a lot of people are used to using altitude, but really, we always sort of wave our hands about what the altitude is because it's really a pressure surface is what we're measuring on.
Yeah, well, one thing like the with the solar zenith angle, the pressure surface also changes. That's
Yeah.
the other thing
Yeah.
you have to remember. So it's like the low solar zenith angle, there is one pressure, and it's a high solar zenith angle, it's a different pressure. Because it's the way how the radiation absorbed by the atmosphere. So
Okay, great, thanks. Very nice talk.
Question? Yeah, I do have a question for you. So this gold emphasis you said at the top has some problem.
oh yeah.
It's too big. Is that just the issue with emphasis that doesn't, accurately capture the vertical variation?
Oh no, this is to do with the perturbations that we get is 160, that is the peak. But most of these perturbations, they don't survive all the way to the upper altitude. So we have to still do some filtering of the perturbation. Like this is the peak altitude of this temperature measurement is 160, as I was saying, 160 around. But then if we set the same perturbation and extend it to the upper altitude, it is not any longer valid because upper altitudes, these perturbations don't survive.
Think about it, it doesn't propagate just vertically, it propagates that horizontally too.
Yeah.
Yeah, but I thought you sort of use emphasis to.
Well,
You're just scaling off of that.
emphasis doesn't know what's happening horizontally. It assumes everything's uniform horizontally.
Okay.
Right, that's the trouble with emphasis. You should do the assimilation, Nick. Your model does it.
Yeah, but this one can be improved like applying some vertical damping or horizontal smoothing factors for upper altitudes.
Another. Again, I was just thinking the thing you said, earlier for the O2 and 2 double vortex, I always thought of it as some kind of indication of horizontal advection transport. Now, if this is really, you said it's a mean average or perturbation around the mean at each grid point, that may tell you more about the vertical motion rather than the horizontal advection, right? Because
So
this doesn't tell you much about horizontal.
this is not against the mean, against quite high.
Yeah, quite, I'm sorry, yeah.
So it's not against the mean.
Oh, not the,
Subtracted, yeah.
not the mean over time.
No.
No, it's a quiet time, same grid point for the quiet day.
Oh,
Day before.
I see.
Yeah, thanks for clarifying.
Quiet time, I see. Does that tell you about the horizontal then? Oh, think about it.
I think when Ben has argued that it does, at least to
Yeah.
a great extent, right?
For one hemisphere, yeah.
Right, yeah, only one.
I was wondering what's the time progression of this vortex, especially in the southern hemisphere. At least in the simulation, there was a strong southward wind from the northern hemisphere push everything towards southern hemisphere. Then there's another wind coming in from the southern hemisphere pushing the uh, atmosphere rotating the other direction that caused this. I don't know whether if the observation do show the whole process of this rotation that he
Yeah, we do have, like on that day, we do have several other scans, and it does show how it is progressing with time. And
in that article, although
yes, it's there in this article. Yes, all this progression is there.
Okay.
Regarding wind, we don't have wind, but when wind reproduce some, and it shows.
Moving from high latitude to low latitude.
yeah.
Okay.
Yeah, there is a movie also in this paper. You can see it there, how it is progressing.
Question? If not, thank you again.